Okay, this is the second chapter 3 lecture. So let's talk about units of concentration. Very important topic in chemistry. In the past, we've been talking about earlier in this lecture about pure substances, meaning it's only water. It's not a mixture of two different things. So in mixtures, we need to distinguish between the components of the mixture. And we'll see that the relative amount of each component determines the overall properties of the mixture. So to understand mixtures, we need some terminology, because now we've got multiple things instead of just one thing like we had before. So first we define a solution. A solution. It's a homogeneous mixture. We learned about that in chapter 1. What a homogeneous, evenly mixed Gatorade, a homogeneous mixture of two or more substances physically mixed together in a uniform way. That's the solution. There are two things in the solution. There is the solute and the solvent. The solute is whatever there is less of. It is the thing being dissolved in the solvent, what there is more of. All mixtures have solutes and solvents. The solvent is, in many cases, certainly with biological systems, water. We're big bags of water. All our cells are mostly by mass percentage water. So that's often the solvent. And you can, as you can imagine, dissolve a variety of solutes in water. It is known as the universal solvent because it dissolves so many solutes. So when the solute dissolves in the solvent, we call it soluble. It is soluble. Sugar is soluble in water. Sodium chloride is soluble in water, dissolves in water. And then you can talk about solubility. Is not everything dissolves completely. There are degrees of dissolving. So for example, if you take chalk and you put it in water, it very slowly dissolves. Very slowly dissolves. So there's the rate of how fast it dissolves and the degree to which it dissolves. Some substances only dissolve maybe half before they remain as solids. So this word is called the solubility. How much of a substance can dissolve in a solvent? And then the last one on here is the word dilute. Dilute. And this is a very important word in the upcoming sections. And it happens, what we're going to do is learn how to dilute concentrations. So when you dilute a chemical mixture, you add solvent, not solute. You add solvent when you dilute a mixture. So there's less solute and more solvent, and that changes its concentration. That's called dilution, and that's what dilute means. So, the basic fundamental unit in chemistry of concentration is molarity, written with a capital M. And it has a very rigorous definition. It's the moles of the solute divided by the liters of solution. It has to be liters. So anytime you're doing a molarity problem, always convert the volume to liters because the unit has to have liters. It has to have moles too. So one way to solve a variety of molarity problems is you read the problem, figure out the number of moles, and then divide by the total volume. And that's the molarity. It's how much of the solute is in the solvent. Now, I've included in this last bullet here a way of rewriting this that is helpful for some problems. And it's simple to do because we learned earlier in this chapter on the periodic table and the formula mass, which is grams per mole. So you can rewrite, you can solve molar mass equals grams per mole. Maybe you want to write this down. Do the algebra, bring the molar mass over to the left-hand side and divide by the molar mass. And you can substitute in for the numerator. Moles is really grams over the molar mass. So you can substitute grams over the molar mass in the numerator, and the denominator stays the same. And by substituting grams over the molar mass, that is an easier way to execute some of the problems that you may encounter. Other problems, you may not need to do that substitution. You may just be able to unpack the problem so that you're able to determine the numerator and the denominator without using this other version. Depends on the problem, as we shall see. So the simple problem here, you're given a 355 milliliter soft drink, and it has 0.133 moles of sucrose. What is the molar concentration of sucrose? So we're looking at this. We have our formula here. Always have the formula for this. We need the moles of the solute. 0.133 is the moles of the solute. We're given that. And we're given the volume of the whole thing in mils. We just need to convert that to liters. We can divide these two numbers, and that makes it a fairly straightforward problem to do. 0.375 written with a capital M. All right, here's another type of problem. Calculate the molarity of a 5-liter solution containing 126 grams. Well, you have the formula, moles of the solute. We're given the grams of the solute. So you need to realize you need to convert grams of the solute, or in this case, this is nitric acid, to moles of the acid. And you do that by dividing by the molar mass. 1 mole is 63 grams. Nitrogen 14 plus 16 times 3 plus 1 is 63 grams of nitric acid in 1 mole of acid. That's a conversion factor that allows you to go from grams to moles. And we see that we have 2 moles of acid. We look at our formula here, and that is the numerator is 2 moles. And we're given the denominator of 5 liters in the correct unit of liters. We divide those two numbers, and we come up with 0.4 moles per liter as the concentration of this solution. All right, here's another example. Calculate the mass of NaOH, that's sodium hydroxide, needed to prepare 1 liters of 1.5 molar solution. So this is one where it's helpful to use the alternative version here. Molarity equals grams divided by the molar mass times liters. And we look at the problem and it says calculate the mass. So we are looking for G. Does everyone see that? we fit the missing variable into what we need, and we see that we're missing G. So do the algebra first. No need to go running for the numbers here. Solve this equation for G. And you would come up with grams equals the molar mass times the molarity times the volume. And you know all three of these things, or you can figure it out because you know the chemical formula, so you can figure out the molar mass. And that number goes right in there. The molar mass goes right in there. That's the molar mass times M. M is the molarity. That should be a capital M, folks. I apologize. Times the volume. And after this point, after you do the algebra here and solve for G on one side of the equation, then it's just plug and chug. Hard to get it wrong after this point. You're just inputting the numbers. It tells you to multiply 40 times 1.5 times 1 to come up with the answer of 60. So this is a nice example where substituting in for the moles of the solute using the molar mass is helpful to solve this type of problem. Here's another one. 960 grams of NaOH is used to prepare a 1.5 molar solution. What is the volume of the solution? So this is a similar type problem. You're given the grams, you're given the volume, you're given the molarity, and asking for the volume. So for those of you listening at home, you might try to solve this on your own. Take out a piece of paper, get your scientific calculator, and try to solve the problem. Take a few minutes to do that. I'm just going to pan ahead. You might pause this recording at this point. And we do adopt a similar procedure. We do the algebra first. We use the other version of the molarity equation. Realize that we're looking for L because it says what volume, that's L in the equation. And you solve the equation for L, and then you plug in chug. Telling you folks that the hardest part of doing the problem is isolating the variable, realizing what variable you're looking for, because you know everything else, and then using algebra to isolate that variable on one side. And after you do that, I believe that is the hardest part of the problem, because if you get it wrong after that point, it's because you're not inputting into the calculator correctly. Okay, so let's talk about how chemistry is done in a lab. In many different experiments, using solutions, mixing things together, chemists need a variety of concentrations. So one experiment, one procedure might call for using 2 molar. Another procedure might be called for using 5 molar. Another for 2.5, and so forth. So what chemists do is prepare a stock solution. This is the basic solution that can be diluted to make the other concentrations. So that's what's in a chemistry filing cabinet, a bunch of stock solutions that are then diluted to the correct concentration that the experiment or the procedure calls for. So what we're learning now is how to dilute a stock solution. The first thing to understand is a dilution is adding more solvent, not more solute. solvent. So you add more water. So let's see the kind of details here. This is a nice slide. I just want you to look at the picture here, and you see the concentrated solution is darker. You've added in progressive amounts of water, and it becomes more dilute. So this is how you change the concentration, by adding some solvent. Here's just another example. Here's some copper nitrate. This would be the more concentrated solution, and they have diluted the solution, so it is now lighter in blue by adding water. So here there is more solvent than solute. We actually know how to make stock solutions. In this class, we've basically learned all the details about how to do that. So let's say you want to make a certain concentration of this stuff here, potassium permanganate. Say it's 1 molar. That's what we're trying to make, is a 1 molar concentration of stock solution of potassium permanganate. 1 molar means 1 mole of solute per liter. So we would figure out the mass of 1 mole of potassium permanganate. I'm not exactly sure that this is a 1 molar solution. I'm not sure if that is the correct mass for 1 mole of potassium permanganate. I don't think it is, actually. But let's just assume that it is. That's the mass of 1 mole of potassium permanganate. You have a special flask here called a volumetric flask that is only good for 1 measurement, and that is 1,000 mils or 1 liter. And you can see that line right there, that thin circle around the end. That is the 1 liter mark. It only measures 1 volume, 1 liter, but it does it very precisely. So to make a 1 molar stock solution of potassium permanganate, you would dump in the number of grams in 1 mole into the flask. That's what's done here on the right-hand side. And you would just fill up the volumetric flask to exactly the 1 liter mark. And there you have your correct concentration of the stock solution. You can see it's a deep purple. So as you dilute it, it will become less and less purple. Here's an important point about the nature of adding more solvent, about the nature of dilutions. And that is shown here. If you take the units of molarity, which is moles per liter, that's capital M. So capital M has units of moles per liter. Moles per liter times liters is moles. That's N, the amount of the solute, N. Going back to the original definition of the molarity, it means moles of solute per liter solution. So molarity times liters is the number of moles, which is the solute. Okay, that's the top equation here, just saying that molarity times volume is the number of moles of solute. Now, look at these next 2 equations. N1 is before the dilution, N2 is after the dilution. So N1 would be the stock solution, N2 would be the diluted stock solution. For the stock solution, N1 is equal to molarity times liters. For the diluted solution, N2 is also equal to its molarity times liters. But here's the thing, folks. Here's the kicker. N1 equals N2. N1 equals N2. Why? Because you're adding solvent. You're not changing the amount of the solute. The amount of the solute stays the same. So if you take this solution here and you add more water to a portion of it, you still have the same concentration of the potassium permanganate because you didn't add any more. The moles of the solute does not change during a dilution. N1, the number of moles in the first stock solution, equals the number of moles in the second diluted solution. So that leads to the dilution equation. This is what is very useful to solve problems of a dilution type. The molarity of the stock solution times the volume of the stock solution is equal to the molarity of the second solution times the volume of the diluted second solution, because the moles of the solute does not change. So this can be extended to any units of concentration that you're using, the concentration of the first one times its volume and so forth. So the first one is molarity explicitly, but you may also see an alternative version of just generalized units of concentration, which are most often molarity. So put this equation in your back pocket. It is what you will use to solve problems. So here's an example. We're given 0.85 liters of 5 molar solution of copper nitrate. It's diluted to a volume of 1.8 liters by the addition of water. What is the new molarity? So this again is another example where doing the algebra first before running for the numbers is a much better way to do the problem. It's clearer, and you will more often avoid silly mistakes. So you look at the dilution equation and you have to identify that, aha, I'm looking for C2, the concentration of the diluted solution. So I solve the equation for C2 by dividing both sides by V2. The V2s cancel on the right side, and I have V2 on the left side, and I rewrite it here, and that is my second line. All algebra. Then you fit the numbers into the equation that you have generated. You can do the units, you should. You can still cross off units here to make sure that your liters do cancel and that you're left with units of concentration, which is moles per liter. So that's a one very nice example of how to use the dilution equation. Here's another one. A stock solution of 1 molar sodium chloride is available. How many milliliters are needed to make 100 mils of 0.75 molar? Now, the first thing I notice about this problem is that the units of molarity, big M, are moles per liter. Always moles per liter, but the volumes that were given here are milliliters. So a nice first step would just be, without even knowing what you're going to be doing, converting milliliters to liters. And then you're seeing that it connects with all the units that you're asked to use in the problem. So you will not be off by a factor of 1,000 for your answer. So that would be my first step here. And the second step would be write down the dilution equation and then look at which variables do I have, which variables am I missing, and isolate that variable doing the algebra, plug in the numbers, check your sig figs. And Houston, we have an answer. So here I'm just fitting the information into the dilution equation. I know that I got my M2 as 0.75, my V2 as 100 mils. And whoops, I kind of jumped ahead here a little bit. I did the math kind of in a different way. I should have had V1 isolated. I realized that I'm looking for V1 in this problem. And I did a whole bunch of steps at the same time here just for teaching purposes. You would have V1 equals blah, 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 just like we had earlier. Then you would go and plug in the numbers. And you see, I also don't like this problem because they didn't convert to liters. And the reason that that works out is because the molarity cancels every time. All the M's cancel. So the only unit that's left is milliliters. So that would be an alternative way to solve the problem. I suggested you convert this to liters first, and then your answer will directly come out in liters. But now the answer comes out in mils. And so I guess that's easier to do because you're right in the unit that the problem is asking for, which is how many mils are needed. So for this reason, I kept everything in mils. Yes, you can solve the problem that way. But yes, you could also solve the problem by converting everything to liters and then converting to mils at the end. Either way. All right, here's another one. If you dilute 175 mils of 1.6 molar to 1 molar, determine the new concentration. So I can see that I'm already looking for C2 because we're given the stock solution. And I recognize that I'm looking for C2 or V2. There's my V2. I should have written V2 in there. Excuse me, C2 or V2 or M2. Sorry, getting my letters confused here. That is M2. And we come up with an answer of 0.28 molar. So very similar approach to dilution problems. You write down the dilution equation, figure out which variable is missing, isolate that variable, and there you go. Okay. Let's end this chapter by talking about other units of concentration. You go to the pharmacy, you see a 70% solution of rubbing alcohol, which is isopropyl alcohol, 70%. That's a unit of concentration. You look on the wine bottle and you see 12% alcohol by volume or just 12% by volume. That's a unit of concentration. On the Clorox container, you see at the bottom right here, sodium hypochlorite, 7.4%. Well, that means by mass. So these are 3 different units of concentration. And they're fairly easy to work with. Well, if you have enough practice anyway. And then I'll talk about another unit of concentration, the environmental unit of concentration, which is parts per million, parts per billion, parts per thousand, parts per hundred, parts per. because frequently we find chemicals in the environment. That's the correct unit to express units from the environment. How many PCBs are in soil? How much fluoride ion is in tap water? Things like that. What is the concentration of carbon dioxide in air? These are all useful ways, parts per million, parts per billion, parts per trillion even. These are the units for those types of things. In the nursing profession, there's even another unit, which is mass by volume unit. And that's what your blood sugar monitor spits out. So there are actually quite a few different units of concentration in chemistry, and it largely depends on the type of solution that you're talking about. Okay. So here is the mass percentage, another type of concentration. And mass percentage, you have to recognize that mass means grams. So we're not talking about moles at all here. And we've already kind of seen this. It's the mass of the component divided by the mass of the solution times 100%. So here's an example, liquid bleach. That's the bottle I just showed you. It says on the label, it's 7.4% sodium hypochlorite. That's the formula for bleach by mass. That's what it says on the bottle. How do you convert that to a molarity, another unit of concentration? Well, you need to know two things. You need to know the density, and you need to know the molar mass. The density will be given, and you can calculate the molar mass from the chemical formula. So to do this problem, you're trying to go from mass percentage to molarity. You would write down the formula first and recognize that mass percentages means that there are 7.4 grams of sodium hypochlorite for every 100 grams of solution, and that this is a conversion factor that allows you to go or determine the number of grams of sodium hypochlorite. Once you know the number of grams of sodium hypochlorite, you get the moles. So we're just trying to unpack the molarity definition, moles of solute per liter solution. So this first line here to get the moles gives you the numerator in the molarity equation. We have 0.1 moles of bleach. And then we use the denominator, the mass of the solution, to go to the volume of the solution using the density as a conversion factor. So here's kind of an abbreviated unit line equation where we see that the grams of solution cancels, and 100 grams of solution is about 98 milliliters of solution. And to install into the molarity equation, you have to put everything in liters. So we convert 98 mils, shuffle the decimal place 3 places to the left, and you get 0.098 liters. You divide those two numbers, round to 2 sig figs because we have 7.4 grams, and we come up with a molarity of 1 molar. So 7.44% by mass sodium hypochlorite, translates into a 1 molar solution of bleach. Here's a volume percentage of example. So the first thing when using these different units of concentration is you write the formula, and then you unpack it by chunking it out, figuring out what the volume of the solute is, the volume of the solution is, what information you're given, and so forth. rubbing alcohol is 70% by volume. If the density is given, how many grams of alcohol are present in a 355 milliliter bottle of rubbing alcohol? So we write down the formula, and I just use the unit line equation. 70% by volume, I unpacked that. That means that there are 70 milliliters of isopropanol for every 100 milliliters of solution, by definition. I'm given, it would also mean that there are 70 liters in 100 liters, but I chose the units of milliliters because I noticed my density is in milliliters and the bottle is in milliliters. So I didn't really need to convert to liters at all in this problem. So I used the 70% by volume as a conversion factor, which allowed me to go from milliliters of rubbing alcohol, milliliters of solution to milliliters of rubbing alcohol. And then I used the density as a conversion factor to go from milliliters of isopropanol to grams of isopropanol. And I come up with 195 grams of isopropanol are contained in this 355 milliliter bottle. So in these types of problems, notice in both these problems, first one we're given 7x by mass. This one is by volume, but in both cases, we had the density. So you need to have that because that is what allows you to convert from mass to volume. Here's another example. I will let you work through this one on your own. I have enclosed the answer, so you should follow this. It's all written out for you, but see if you can replicate this on a separate piece of paper. If you can, you're on your way to mastering this topic. So let's talk about the last unit of concentration, which is ppm, ppb, ppt, as I was saying. And this is very common units in the environment. You're seeing, if you want to know the concentration of lead in your tap water, that would be given as ppbs. And then you would compare the EPA, our Environmental Protection Agency, has established minimum levels above which can be toxic, below which you're okay. So we have many environmental applications for parts per units. So here are sort of the definitions. These are mass-based definitions. You can have different applications by volume, there's by volume, by mass. There are other ones as well, but mass and volume are the two basic ones. So we'll stick in this class. We'll use volumes and or masses, either one of those two. So based on mass, it's just the mass of the solute divided by the mass of the solution, the total mass of the solution, times 1,000,000. That's ppm. Same thing, but times 10 to the 9th is ppb, parts per billion. ppt, parts per thousand, would be mass of the solute divided by mass of the solution times 10 cubed. So you can see the pattern here. Parts per million means times 10 to the 6th. Parts per billion means times 10 to the 9th. So let's see how this is applied. Here we see the concentration, looking for the concentration of parts per billion in PCBs, polychlorobiphenyls. Those are toxic compounds that leak out from a chemical spill. Happens in many industrial processes, produce PCBs, and they spill into the river, they get in the soil, they get in the oceans, and they contaminate everything. And so this is where the EPA has to step in and says, what's the lower limit on the amount of PCBs that can be contained in soil? So figuring out the concentration of the PCB is very important. So you're given that there are 0.06 milligrams of PCBs in 4,600 kilograms of soil. What is the concentration of PCBs in PCBs? We got PCBs, PCBs, I'm getting all confused. Hopefully I'm not confusing you. So we take this apart. I'm using this equation here, mass of the solute divided by mass of the solution times 10 to the 9th. We're given the mass of the solute, that's the 0.06 milligrams. We're given the mass of the solution, that's the 4,600 kilograms. And I just converted everything to the same unit. Doesn't matter which unit you convert it to, as long as they are the same. Just have to be the same. So I chose to convert everything to grams. So I converted milligrams to grams and kilograms to grams. I then divided those two numbers and I multiplied by 10 to the 9th. 1 times 10 to the 9th is the same thing as 10 to the 9th. It's just that when you input it on your calculator, often you do it as 1 exp 9. And I come up with my answer here of 0.01 ppb. So what does that mean? The interpretation is that if you had 1 billion molecules of soil, 0.01 of them is a PCB. So it's 0.01 parts in 1 billion of the solution, which in this case is the kilograms of soil. That's what it means. When we see that the concentration of CO2 in the atmosphere is 400 parts per million, that means that out of 1 million air molecules, 400 of them is CO2. Here's another example. EPA has a limit of 2 ppm fluoride in drinking water. Let's say you're at the water plant and you're fluoridating the water, and you fluoridate by adding 32 milligrams of sodium fluoride for every 20 kilograms of solution. Are you above or below the limit of fluoride, which can be in drinking water? So you're given the mass of the solute in milligrams, you're given the mass of the solution in kilograms. You do the same thing, you divide those two numbers, but this time you're in ppm, so you're multiplying by 1 million. And I didn't draw all this out. This is one you're supposed to do on your own. And if the number that you come up with is below 2, you're okay. If it's above 2, you would need to dilute it more by adding water. So those are the final units for this chapter. And that is the end of chapter 3. Good luck, everyone, doing the homework problems. As always, let me know if you have any questions.